the ultimate guide to launching a rocket to Mars.
Unlike most forces, gravity does not require objects to be in contact in order to have an effect. The scenario above shows forces that require contact, while the one below shows forces that do not require contact. Gravity originates from the center of the Earth. If we were to hold a plumb line above the surface of the Earth, we can say that the plumb line would pass through the center of the sphere. The same goes for all other plumb lines on other parts of the Earth. Now, if we were to have three different scenarios. Firstly, on Earth, when two objects, one with twice the mass of the other, are suspended from two identical spring balances, which measures their weights, the spring balance with the heavier object will record a value that is twice the value of the other. Alternatively, if we place an object that is hung on a spring balance on Earth and on the Moon, the spring balance will record a higher value on Earth as compared to the Moon, as the Moon has a lighter mass than the Earth. Lastly, when an object is placed further and further away from the Earth, the gravitational pull on it decreases. More specifically, the effective gravitational force is proportionate to 1 over r squared. From these examples, we can see that the gravitational force of an object is proportionate to the mass of the object as well as the mass of the planet. Also, it is proportionate to 1 over r squared, where r is the distance between the object and the center of the Earth. Thus, F is proportionate to mass of object times mass of planet over r squared, which is also known as F proportionate to m1 m2 over r squared. This equation shows that any two objects will exert a gravitational force. Given that F is proportionate to m1 m2 over r squared, we want to find the constant that equates F to m1 m2 over r squared. This constant is known as g. In fact, the constant g is equals to 6.6726 times 10 is the power to negative 11 Newton meter square per kg squared. But this is not entirely accurate. This value is very small, and as such, it reflects the weakness of the gravitational attraction by objects of small mass. The gravitational field strength G at a point is defined as the gravitational force per unit mass at that point. To find G in terms of R, we equate m1g to g m1 m2 over r squared. If we divide both sides by m1, then G is equals to g m2 over r squared, and G is proportionate to 1 over r squared. Given that the closeness of the lines represents the gravitational field strength, the closer the object to the Earth, the stronger the gravitational force. Alternatively, if we plot a graph of G against R, it will look like this. Imagine if two stationary planets were placed within each other's gravitational field. The two planets will experience a pull towards each other. They will accelerate and eventually collide. In the case of the Moon and the Earth, both the Moon and the Earth exerts a force on each other. However, have you wondered why the Moon doesn't collide onto the Earth? Based on instinct, you will know that it has got to do with the Moon revolving around the Earth. So what is going on? Basically, if we look at a simple setup, we can understand what is happening. Imagine a car that is traveling forward. When a force is applied to it, perpendicular to its motion, the car would turn in that direction. Similarly, a car that has a string attached to its front is moving in a straight line. However, if we decide to pin the string down at a point, the car will experience a force that is constantly perpendicular to its motion, and the car would then move in a circle. A release in string will lead to it continuing in a straight line. The car will not spiral inwards when it is tied to the string because its original motion is to move forward. Thus, it can be implied that it is constantly trying to escape, preventing it from spiraling inwards. The Moon is like the car that is always moving forward, and the gravitational pull from the Earth on the Moon acts like the string and keeps the Moon in a circular motion. In fact, this force is known as centripetal force. The equation for this force is F equals to mv squared over r. In the case of orbiting planets, there is no string to prevent the planets from escaping their orbits. Thus, it is important that the velocity of the planet and the radius of the rotation is exact, and this prevents the planet from escaping from its orbit. Now, back to gravitation. We will find out how to calculate gravitational potential energy of an object under a varying gravitational field. Basically, the term potential energy refers to the energy an object potentially has. We are familiar with the use of GPE equals to mgh, but that is only assuming that G is constant, which means that it is under a constant gravitational force. However, for an object that is placed far away from Earth, the gravitational force on it is not the same. If we were to place an object at an infinite distance away, it will experience no gravitational pull and thus zero gravitational potential energy. Based on conservation of energy, energy is converted from one form to another. So, as the object travels from Earth, its gravitational potential energy is converted to other forms of energy like kinetic energy. Thus, GPE decreases as the object travels closer to the Earth. As mentioned before, the gravitational potential energy at infinite distance is 0 joules. Thus, as the object travels closer to Earth, the object's gravitational potential energy decreases from 0 joules, making it a negative value. Thus, we can imply that the formula for GPE gives you a negative value, and physicists have found that the formula for GPE is negative gm1 m2 over r. It is similar to the formula for gravitational pull, except that the radius is not squared. So based on this equation, we can plot a graph and we can see that GPE decreases exponentially as an object becomes closer to Earth. If we were to calculate the total energy at a point, it will be given by half mv squared plus negative g m1 m2 over r. Now, I will introduce a new term called the center of mass. This term refers to a unique point in an object or system which can be used to describe the system's response to external forces. So for example, if we were to have the center of mass of a box of uniform density, it will be right at the center of the box. For a cone of uniform density, it will be somewhere near the base of the cone since the base has a larger mass as compared to the top. So if I have two objects instead, and let's say one box is heavier than the other, the center of mass for the two boxes will be nearer to the big box. In the case of the solar system, when two planets orbit around each other, they rotate about their center of mass of the two planets. Taking this a step further, we now look at an object that is of negligible mass as compared to Earth. The object will revolve around the Earth, and the center of mass is very close to the center of the Earth. However, if I have two planets of the same mass instead, they will rotate about each other, where their center of mass is right in the middle. So in the case of the Earth and the Moon isn't of negligible mass as compared to Earth, and neither is it of the same mass. Thus, the center of mass will not be at the center of the Earth, and neither will it be right in the middle of the two planets. It will be in between the two planets, but nearer to the Earth. Therefore, the two planets will move in a motion like this. When a force of constant magnitude is applied on a box, the box will accelerate since F equals to ma. In other words, its velocity increases constantly with the force. The longer the force is applied to it, the greater the change in its velocity. Given that 3 newtons of force is applied to an object of mass 1 kg, the object's velocity will change according to its acceleration, which is 3 meters per second squared. Thus, the velocity of the object increases by 3 meters per second every second. So after 3 seconds, the velocity of the object will be 9 meters per second. Now, I will introduce a new concept called momentum. Momentum is given by the equation momentum equals to mass times velocity. Basically, I like to see momentum as a tool to help measure the impact of the force exerted on the object. Linking force to a momentum, we can see that when a constant force is applied to an object of constant mass, the object's velocity increases constantly, thus its momentum increases constantly as well. A constant force will cause a constant increase in velocity and thus a constant increase in momentum. In summary, the net force acting on a particle is equal to the time rate of change of the momentum of the particle. But in the case of rocket propulsion, we are dealing with an object with changing mass, but of constant velocity. Thus, the equation F equals to ma is irrelevant in this situation, since a is equals to 0. To fully understand this effect, we have to first understand a few concepts. Firstly, we have to understand the term relative velocity. Imagine if we have two boxes, box A and B. Both are moving towards the right, except that A is lower than B. Now, if we were to focus on box B, it will look as though box A is moving towards the left. This concept is known as relative velocity. Similarly, when we observe a rocket up close, the fuel is ejected at the back of the rocket, propelling it forward. The velocity of the fuel relative to the rocket is in the opposite direction, so let's call this relative velocity Vx. However, we must know that the velocity Vx is only relative to the rocket. The rocket itself is still moving. Thus, although it may seem as though the fuel is traveling in the opposite direction from the rocket, the fuel is actually also traveling towards the right-hand side, but at a slower rate than the rocket itself, when from looking afar. The velocity here is termed as the velocity relative to the coordinate system. Now, we represent the fuel of the rocket as a point. Given that the velocity of the rocket is v, and the relative velocity of the fuel to the rocket is vx, the velocity of the fuel relative to the coordinate system, v fuel, would be v minus vx, which makes sense since the fuel is traveling at a slower rate than the rocket. The second concept would be to understand how a force will affect the rocket with changing mass but constant velocity. The mass of the rocket would decrease with time. Thus, it can be expressed as m plus dm, where m is the initial mass and dm is the change in mass. dm is negative since the rocket's mass decreases. The mass of the fuel ejected will be negative dm, it being a positive value. Thus, the momentum of the rocket will be m plus dm multiplied by v plus dv, where dv is positive since its velocity increases. The momentum of the fuel is negative dm times v minus vx. The total momentum will be m plus dm times v plus dv plus negative dm times v minus vx. A law of conservation of momentum states that the total amount of momentum of a system is constant provided that there is no external force acting on it. The initial momentum of the system, where the rocket has not ejected fuel yet, will be mv, where m is the mass of the rocket and the unburnt fuel, and v is the velocity of the rocket initially. Since the momentum is conserved, the momentum before and after the fuel is ejected should be equal. Thus, mv is equals to m plus dm times v plus dv plus negative dm times v minus vx. This equation can be simplified to m dv equals to negative dm vx minus dm dv. However, the term negative dm dv is a really small value and it is a product of two small values, thus it is negligible. If we were to divide the equation by dt, it will become like this. Thus, ultimately, dv dt will be the rate of change of velocity, which is also acceleration, while dm dt will be the rate of change of mass of the rocket. Indirectly, ma will give you force. Thus, this equation, F equals to negative Vx dm dt, will represent the effect of the thrust force on the rocket. Now, we can see that when a rocket is launched into space, it is possible to move. Even though it has nothing to push against, the law of conservation of momentum will help the rocket to propel forward. Imagine a rod that is pinned at its center and assume that there is no friction. If a force is applied to it, it will spin. So based on F equals to ma, when a force is constantly applied to it, the rod will accelerate, and the moments about the rod will be F times r equals to m times a times r. If you were to express the moments in terms of velocity, it will be moments equals to m times r times dv dt. Based on Newton's first law, it states that an object with no net force on it will remain in its state of motion. Thus, if a rod was rotating initially, it will continue to rotate at a constant velocity unless a force is applied to it. Thus, the equation m times r times dv dt wouldn't work since dv dt is 0. If we link this to angular momentum, it will go like this. The angular momentum L will be L equals to m times r times v, which is a constant, since its mass, radius, and velocity remains the same. In fact, this equation, L equals to m times r times v, can be expressed in another term, L equals to m times omega r squared. The term omega refers to the radian per second. Basically, radian shows the ratio of the arc of the circle to the radius of the circle. So the greater the radian, the greater the angle in a sense. With this understanding, radian per second means the angle covered per second. Let's say an object is being swung around. The value of omega will be calculated by taking 2 pi over t, where 2 pi represents one complete revolution and t is the time taken to complete one revolution. So if we multiply omega to the radian, it will be equivalent to finding the length of the arc travelled in 1 second, since omega is the ratio of the radius travelled per second. This gives its velocity. Now, back to the equation L equals to m times omega r squared. We can derive it from L equals to mvr by replacing v with omega r. Finally, after going through all the concepts, we now look at the path the rocket takes when it is launched to outer space and eventually to Mars. When a rocket is launched initially, it is launched in a straight line. This is to minimize the time taken for the rocket to pass through the thick layer of atmosphere, as it requires a lot of fuel to be burned to propel the rocket through the atmosphere. As shown in the diagram, we can compare that a straight path will be much faster than a curved path. After the rocket escapes the atmosphere, the rocket is then tilted to the curved path. A lot of necessary calculation is necessary for this process because we want to bring the rocket to an orbit around the Earth before having it to go to Mars. As mentioned before, when a planet orbits about the other, the velocity and radius has to be very accurate. If not, the planet will either escape the orbit or spiral inwards. Similarly, we have to ensure that the radius and the velocity of the rocket are correct to allow it to orbit around the Earth. Assuming that we have the correct values, the path of the rocket from launch to a low orbit will look like this. After going to a low orbit, the rocket will have to move to a larger orbit. Basically, what we want to do is to get the rocket to move from a circular path to an elliptical path and eventually go into a circular path again. For the rocket to move from a circular orbit to an elliptical orbit, it has to increase its velocity. And for it to move from an elliptical orbit to a circular one, it has to increase its velocity as well. This concept of transferring from orbit to orbit is called the Hohmann transfer orbit. It is a concept that is widely used even for launching a rocket from Earth to Mars. Basically, to see what happens when a rocket travels from Earth to Mars, we have to understand what is going on. Earth and Mars both revolve around the Sun. Basically, after the rocket is launched and is orbiting around the Earth, what we want to do is to get it to travel an elliptical path to Mars and eventually orbit around Mars. And this basically is the Hohmann transfer orbit as well. I will not be touching on the concepts of the Hohmann transfer orbit as it is very complex. Although it may have sounded simple, please note that we have to take into account the effects that other factors, like gravity, have that will affect the path of the rocket. However, I hope that this animation has given you a rough idea of the concepts involved in launching a rocket to space. Thank you.